Quantum transformation. TiS3 nanoribbons become superconductors under pressure. The authors have made the discovery during their painstaking search for new materials that can transmit electricity without loss of energy, a hot topic that has for long haunted the scientific community. Our research focuses on one such promising material, TiS3 nanoribbons, which are tiny, ribbon-like structures made of titanium and sulfur. In their natural state, TiS3 nanoribbons act as insulators, meaning they do not conduct electricity well, says Mahmoud Rabi Abdulhafez, an associate professor at University of Sharjah's Department of Applied Physics and Astronomy. However, we discovered that by applying pressure to these nanoribbons, we could change their electrical properties dramatically, adds Abdulhafez, who is the study's main author. Experimental findings. The scientists exposed TiS3 to gradual pressure. As they increased the pressure, they found that the TiS3 system underwent a series of transitions, from being insulators to becoming metals and superconductors, for the first time. TiS3 materials are known to work as good insulators, but it is the first time scientists have discovered that under pressure they can function as superconductors, paving the way for the development of superconducting materials. Superconductors are special because they can conduct electricity with zero energy loss, which is incredibly valuable for technological applications, says Abdulhafez. But, imagine a world where electrical power could be transmitted without any energy being wasted as heat. This would revolutionize how we use and distribute electricity, making everything from power grids to electronic devices far more efficient. It is exactly this potential which the authors tout as a breakthrough. The potential of TiS3 to turn into materials causing no waste when transmitting electricity. By carefully controlling the pressure applied to these materials, the authors identified the exact points where they changed from one state to another. This is significant because understanding these transitions helps us learn how to manipulate other materials in similar ways, bringing us closer to discovering or designing new superconductors that can operate at higher temperatures and more practical conditions. On the method adopted to conduct the study, the authors write that they pursued experimental and theoretical approaches to comprehensively explore the high-pressure behavior of the electronic properties of TiS3, a quasi-one-dimensional, Q1D, semiconductor, across various temperature ranges. Through high-pressure electrical resistance and magnetic measurements at elevated pressures, we uncover a distinctive sequence of phase transitions within TiS3, encompassing a transformation from an insulating state at ambient pressure to the emergence of an incipient superconducting state above 70 GPa. According to Abdulhafez, the study paves the way for finding new superconductors, the hunt for which he likened to the search for the Holy Grail in materials science because these materials can conduct electricity without any energy loss. This is crucial as it could lead to incredibly efficient power transmission and numerous technological advancements. However, the authors note more research is needed to understand how these superconductors work and the theories behind them, topics which are still hotly debated in the literature. In our research paper on TiS3 materials, we found that we could change their electrical properties dramatically. These materials have the potential to revolutionize power transmission by enabling electricity to be conducted without any energy loss. Additionally, they could advance technologies in medical imaging, electronic devices, and transportation systems such as maglev trains, says Abdulhafez. The authors are upbeat about the implications of their findings. They note, our findings provide compelling evidence that superconductivity at low temperatures of tilde operator 2.9 K is a fundamental characteristic of TiS3, shedding new light on the intriguing high-pressure electronic properties of TiS3. Thank you for watching. Please subscribe, like and hit the bell icon.